Hello students, we're continuing our study of universal gravitation. The first topic is satellite motion. So we're the beginning of the idea of the universal gravitation force law came to Isaac Newton when he was outside of London. Actually, he had escaped London that was experiencing the plague. And so he had the opportunity to get away and maybe save his life. And he stayed with a relative that owned an apple farm. And so he had a lot of time on his hands. And the story goes that he was under an apple tree and he saw the moon up above him. And he, at that point, people understood, Isaac Newton understood, that the moon goes around the earth. But what was puzzling him was that he knew about inertia. He knew this was Galileo. If you believed what Galileo was saying about inertia, the moon really should just go in a straight line. But for whatever reason, it was going around the Earth, and Isaac Newton was trying to understand, how can the moon go around the Earth? There must be some force pulling on the moon. At that point, people didn't understand that whatever gravity is, it was also pulling on the moon. Nobody had that idea until Isaac Newton, sitting under the apple tree, the story goes, saw an apple fall. And he's thinking, the apple is falling because of a gravitational force. Maybe not those exact words. And then he thinks, wait a minute, could that gravitation force be pulling on the moon? And I think that at that point he immediately realized, he must have the answer, because if you think about it that way, the moon is falling towards the Earth, but at the same time it has tangential motion. So instead of falling straight down to the Earth, it will ultimately fall around the Earth. And so from there comes the ideas that you need to predict the orbits of the moon around the Earth. And here comes the universal part. You can also predict the motion of the planets around the sun. The planets are falling towards the sun, but no, they have tangential motion as well, so they're falling around the sun. And while we're on the topic of universal, right, this is universal gravitation, the Earth's gravitational field actually goes way out. It affects the moon, but it also pulls on the other planets. It even pulls to some tiny amount on the other stars in our galaxy. So the gravitational pull of objects like the sun, the Earth, and so on go out essentially infinite distances. And so that's where the universal part of this topic is coming from. Now let's get back to satellite motion. Let's get back to the moon and how it is going around the Earth. So one way to explain it is, think about what happens. First, think about you've got a baseball, all right, and you just drop it 5 meters, and I realize that G is 9.8, but let's suppose that G were just slightly different. Let's say it was just 10. So if G were exactly 10, it would take exactly 1 second for this thing to fall. So 1 second later, it falls and hits the ground. But let's suppose that you threw it with a horizontal velocity component here. You throw it horizontally at 20 meters per second. Then in 1 second, it will have gone a horizontal distance of 20 meters, but in that same second, it will also have fallen the 5 meters, and it's going to end up here. So it its path actually describes a parabola like that. Let's suppose now that you threw that same ball with a velocity of 8,000 meters per second. Then it would fall. It would still fall the 5 meters, right? When it's gone 8,000 meters this way. But the thing is, though, that the Earth's curvature out at 8,000 meters makes the Earth's surface go down 5 meters. So what will happen is the ball, instead of just falling straight down or going straight, it's actually describing this motion here. Your baseball, which is now going, at a ridiculous speed, and of course we're ignoring air friction here in this scenario. But anyway, your baseball will have orbited the Earth. I'm going to stop here because I've got a little demo that I want to show you. This diagram is from Isaac Newton's book on universal gravitation. And in it, we can see how he thought of the idea of artificial satellites. The idea is that you've got a very tall mountain, and so tall that it gets you up above the Earth's atmosphere. And you give a cannonball, you've got a super powerful cannon, and it gives the cannonball enough energy, enough velocity to fall around the Earth, so to speak. So let's give it a try. The red dot is the cannonball. Let's make it go. So that was at a starting velocity of 3.3 something kilometers per second. I should caution you that these numbers are not quite right. Anyway, it's still a good demo. So it ended up hitting the surface of the Earth here at location D. Let's increase the velocity here. Let's make it go a little higher. Let's try it like that. All right, and try it again. And now, okay, we've gotten a little further. That was at 4.2 kilometers per second. Let's try a little bit more speed. Here, let's try. Okay, we'll try that. And what happens? Oh, still not enough. Let's go higher. Let's try. Let's try this one more time. Oh, looks like 7, or actually, in this simulation 7. I think it really should be 8, but the simulation's not perfect. Anyhow, watch what happens. So this is an important point. Satellites, when they go orbiting around the Earth, they come right back to where they started from. The only thing is that the Earth is rotating. So if you were on the Earth, the cannonball wouldn't hit you in the back of the head unless your mountain were at the North Pole. Okay. Now, let me show you something else about this because this will become relevant later on. Let's suppose I increase the velocity even higher. I want to point out that at this velocity, at this starting speed, the altitude of the satellite was constant, and it was the same distance from the surface of the Earth to its path. But if I increase the velocity, the starting velocity, let's see what happens. You see? later on, we're going to think about this in terms of having more energy than you really need. And so you'll notice that it went farther away from the Earth, so it had more potential energy at that point. Yeah, right. Sorry about that. Now, the other thing that to notice about this, let's do it one more time, is that the first orbit that I did, which was at just the right speed, that was a circular orbit. But now this, and we're going to talk about this quite a lot, this is not a circle anymore. The path of the red dot is actually an ellipse. It's an elliptical orbit. Yeah, so I'll spare you the guy getting hit in the head. All right, thank you. All right, back to the regular notes. So now you have seen Newton's canon. Now, the speed that you need to make that cannonball have a circular orbit around the Earth is given by this formula. The orbital speed is the square root of the universal gravitation constant times the mass of the Earth, right? Okay, so I guess I should have made this a capital M, M sub E, to use our book's notation. And then R is the radial distance from the center of the Earth to the orbit. All right. Now, how can we find this formula? Let's look at this. Now, one of the most straightforward ways to think about it is to think of that the Earth, the gravitational pull of the Earth is acting like it is providing the centripetal force of the satellite. So you've got your satellite going around the Earth. I've labeled it the moon, so the moon is a satellite of the Earth as well. And the string here, the tension in the string, represents gravity. It is the centripetal force that makes your satellite go in that circular orbit. Now, I want to point out that the Newton didn't approach the problem this way. It makes sense for us to think about it this way, given what we've already learned. But this isn't what Newton thought. Also, one reason is that Newton knew that the orbits of the planets around the sun and actually the orbit of the moon around the Earth, it's not a perfect circle. These orbits are actually elliptical, and there is a story. So let's see, I've got some dates here. Galileo lived from 1564 to 1642. And at that point, there's this huge controversy as to whether or not the Earth is the center of the universe. Galileo faced the Inquisition. He could have died for his heretical views, his view that the Earth was not the center of the universe. And instead, his idea was that the sun was at least the center of the solar system, maybe not necessarily the universe. Then we had Tycho Brahe, who lived from 1546 to 1601. So he actually lived before he overlaps with Galileo. But his life goal was to prove that that Copernicus, Copernicus thought that the planets orbited around the sun, and Copernicus thought that the orbits of the planets around the sun were perfect circles. And Tycho wanted to prove that Copernicus was right. And Galileo also believed that the planets orbited in perfect circles around the sun. And so Tycho set up a fabulous observatory. It didn't have any telescopes, but it had amazing devices for measuring the exact locations in the sky of the planets. And he took tremendous amount of notes. And the problem was he could never succeed. He just couldn't prove that the planets moved in circles, perfect circles around the sun. Now, he had a student, Johannes Kepler, and who lived from 1571 to 1630. And this student was a very different person from Tycho. Tycho was, the ultimate observational person. He would write down very precise numbers and so on. Kepler was not good at doing that sort of thing, but he was really good at math. When Tycho died, Kepler he grabbed the notebooks of Tycho. There's another story there. There's lots of stories. For example, why is it that he's called Gold Nose? You see, Tycho happened to have, well, this is a picture of Kepler, but Tycho got his nose cut off in a duel. So you go look it up. Anyhow, Kepler takes Tycho's notebooks, and so this is Kepler right here, and looks at them for years. And little by little, he realizes the mistake being circles. No, the planets are not going in circles. And so Kepler figures it out. They're really going in ellipses. So I want to compare in the geometry of circles and ellipses. I've got here a circle drawn, and the origin of the XY coordinate system is right here. And the thing is that the distance from the origin to the circle is the same this way and up and down. And the formula for the circle is right here. It's x squared over r squared plus y squared over r squared equals 1. The formula for an ellipse is almost the same. The difference is that the distance from the origin out to the ellipse is longer one way than the other way. So this is distance A, this is distance B, and your formula is x squared over a squared plus y squared over b squared gives you 1. They're very, very similar things. The A distance here, the longer distance, is called the major radius, and the B distance is called the minor radius. I got to caution you that there's other terminology here, like the major axis, semi-major axis, and so on. So the geometry of ellipses has a lot of terminology, but at least these two things are simple. Now, one of the features of ellipses is the idea of foci. Now, you've heard of the idea of a focus in this context. Let's say, let's get some space here. If I have a beam of light, right, light rays going like this, and I have a lens, I'll draw a lens here, right? And then you let the beam of light go through, the rays of light will do this. Come along. And do that, and do that. This point right here is called the focus. Well, a ellipse has the same effect. Imagine that you made a mirror. Uh, the mirror is not the full ellipse. Instead, the mirror is just this much of, right? So you have a piece of glass that's elliptically shaped, and you have your beam of light coming along, just like before. So here comes your rays of light, and they bounce off of the mirror. Here comes another beam of light. This is challenging to draw just right. Like that. This one needs to keep going. All right, I'll do a couple more. A beam of light, like so. I kind of missed the focus on that one. Ooh, like that. Okay, so anyway, the idea is that the focus is right there. Ellipses actually have two focuses. There's one over here. Okay. Now, yeah, here's a way of drawing perfect ellipses. You put two thumbtacks into your desk and put a loose string around it, and run your pencil around the two thumbtacks, letting the string guide you. You'll get a perfect ellipse, and the thumbtacks location will be where the two foci are. So, Kepler, being a mathematical whiz, looks for geometrical things about the orbits of the planets. And the first thing that he discovers is, yes, the planets are moving in ellipses around the sun, and to go with that, the sun is at one of the two foci. So this is a very important point. The sun is the focus of the ellipse. Now there is another focus, but this focus has no meaning at all. If you point a telescope there, you'll find nothing is there. Okay. Now another important thing to kind of keep in the back of your mind is that this description is valid because the sun is much heavier than the planets. In fact, the sun moves also, and what is really at this focus is not the center of the sun, but rather the center of mass of this entire system. But that's getting into some little details that I don't think we need to worry about right now. For now, the sun is so massive compared to the planets, you might as well say, yes, the sun, the middle of the sun, the center of the sun is at the focus. So Newton understood, so Newton knew about Kepler's, this is called Kepler's first law. Newton knew about it, and so he realized that if you did the cannon on the mountaintop satellite idea, the center of the Earth would be the focus of the ellipse that the cannonball is doing. So he understood that. All right. So I think that this is a good place to stop. Thank you for watching my video. See you later.